and he'll still be here for a few days in case you want to catch him for coffee around the CFA before he goes. And Lucas, the floor is yours.
Awesome. Thanks for the intro.
One quick comment before we continue, Lucas. So I've told you this before. So it's the way this thing is set up is as a discussion more than the speaker just talking all the time. So don't be too surprised if you get interruptions along the way. We encourage people to ask questions all the way through. So.
Absolutely. And in fact, I do have some, as you'll hear later, I have some code that can be run sort of on the fly. So if we wanted to demonstrate anything at any point, provided we have the time for it, I'm happy to do so and or stay after. Yeah, thanks for the intro. As Vinay and Raphael said, I just finished my master's at Sorbonne and Institut d'Astrophysique de Paris. I was working with these fellows here on the left, Ben Wandel, Tom Charnock, and Justin Ousing. They probably dropped in this meeting from time to time. And what we worked on was sort of very long title, but lossless scalable implicit likelihood inference, ILI, for cosmological fields. But I guess sort of a better and quippier name for the project would be how to compress the universe down into a few numbers and then what to do with them. So I'll explain sort of the logistics behind it. So the motivation behind projects like this and simulation-based inference is we have a lot of new cosmological and astrophysical data being expected to be dropped in the next couple of years. So for instance, Euclid and the Square Kilometre Array are giant redshift surveys in the optical and radio regimes respectively, with more than 1 billion galaxies each. So lots of sources, and what the end goal, at least for cosmologists, is to map out a cosmological density field. So you observe the universe and you observe some brighter regions in clusters and tendrils of galaxies in this cosmic web, and then you observe the complement to that set, which is the void. So this forms this massive structure that we really want to understand, at both early times and late times. But the really tricky thing is that we don't really know how this is distributed. We have lots and lots of models, both numerical and analytical, for how this structure forms from a relatively smooth Gaussian field, the CMB, cosmic microwave background, like everybody here is very familiar with. But we don't know exactly how that forms. So the idea behind this endeavor and most cosmological analyses in the next decade are going to be how to fit these really, really technical models to this really, really massive set of data. So I'm sorry, my cursor is there. Okay. So what this posits is sort of an inverse problem. So we have a model or a simulator, something that can generate realizations of the universe in silica, like in our on our clusters. And the whole idea is, so given a set of input numbers, these parameters, whether they be cosmological parameters, a baryon fraction, or whatever, what is the probability of what is the distribution of these parameters that best describes the observed data? So this is what I'm without writing it down, I'm describing Bayes' rule, which everybody learns in your intro statistics. This is an inverse problem, and it's really tricky. It's really just figuring how to fit these massive simulations to data. So some things I want you guys to keep in mind before as I get through this presentation is, can we obtain distributions for cosmological parameters, so the posterior distribution for a given cosmological model, making use of the full overdensity field. So all those galaxies, if you arrange it into a density field, a sky survey, can we use all of that information to provide the tightest constraints of cosmological parameters? And on a sort of side note, can we quantify the information content of this field? These are things that we're going to sort of build towards. So this is sort of the end goal. What we want to do is provide constraints on contentious cosmological parameters directly from the overdensity field, and hopefully resolve some tensions. Right now, there's, as everybody knows, there's a big tension between early time universe models, CMB fits to data for these cosmological parameters, and late time fits to the data like supernovae. And the intermediate stage of the universe is what we're going to be able to see for the first time very, very shortly, fingers crossed. And we want to fit these models and hopefully reconcile those differences. So this is, again, for you guys, this is a pretty general talk, but for statisticians, this is going to be sort of a review. But we have Bayes' theorem, which describes the posterior distribution of parameters of theta given some observed data, and it's proportional to the likelihood of the observed data. So this could be a Gaussian distribution, binomial distribution, or in our case, a simulator that describes realizations of the universe times the prior distribution, whatever prior we impose on the parameters of interest. So what we're talking about here specifically is simulation-based inference. So this is when we can't write down just a normal distribution to describe our massive sky survey. So this is, and we've coined the term implicit likelihood inference because the whole idea is if you have a simulator, a way to realize, to generate stochastic realizations of a set of data, you implicitly have a likelihood. And we'll review a little bit of simulation-based inference. What's really cool about simulation-based inference is that you can forward simulate all kinds of wacky effects that are really hard to write down analytically. So in the case of sky surveys, you can write down models for, you can forward simulate models for dust, for observational effects, incomplete surveys, and sort of get rid of those effects all in one go. And those will have an impact on your final inference for your parameters. When you write down these things analytically, you end up having to derive really funky covariance matrices to take into account sort of these non-cosmological effects, so things on top. So what it does is sort of puts the challenge of the inference problem into forward simulation, and then figuring out how to do that efficiently. So we'll get into that. And the big con, the big drawback to simulation-based inference is how do you compare the distance between your observed universe and your simulated ones? Because you have billions of galaxies, as we said before, and we don't a priori have a perfect way of condensing that information. And then this is sort of what we're building towards. So simulation-based inference, again, for the stats crowd, this is pretty bread and butter these days. So essentially, so what you do is you observe some data, and you come up with some compression or representation of that data. If it's small enough, you can just use the data as is. But then you create a simulator, you draw parameters from a prior, and you generate a whole bunch of simulations, and you compare the distance of all of the simulations to the observed data. And you define a somewhat arbitrary acceptance criterion, this epsilon. And then if your distances fall below or equal to this arbitrary distance measure epsilon, you keep the simulation and you record that parameter value that you simulated your data with. So in our case, our simulations are, in this case, are going to be just two-dimensional mock dark matter skies. So here, these are just 128 by 128 images. But this is just an example of a sketch of where we're going. But the problem is with these, with real large-scale structure simulations and data, you can't just take the mean of the field. And as we'll see, the power spectrum or the variance, the scale-dependent variance of the field, is not a super good descriptor of all of the physics that's happening under the hood, or really the underlying cosmological parameters in all cases.
Question?
Yeah.
So for 2 or 3 parameters, this is not going to be a problem. But I was wondering, how do people make sure that the simulation grid that they generate actually is sufficient, meaning that there are no gaps in the simulations which might be a better explanation of the data, but because there's only a finite number of simulations you can do, you're going to miss it, right? So what Is that a concern? I mean, is that something that people have to worry about?
So is the question how do you know how many simulations you need?
Yeah.
Or so I think that is sort of an open question. This is what we're hoping to answer in this framework. So it's honestly kind of dependent on how fat your prior is. So if you have a really, really big prior or a really high dimensional problem, you're going to need a lot more simulations, right, to cover the, to cure, well, mitigate the curse of dimensionality and navigate that space, depending on where your observed data is. So if your observed data is in, the corner of a hypercube, then you're going to need a lot of simulations to fill that volume in order to cover that region. And in this framework, this is exactly one of those questions that we're working towards trying to answer for a high dimensional parameter space and a very high dimensional data realization.
I almost feel like Vinay's question, more than how many simulations you need, actually means how do you know that your model is correct? In the sense that, you're saying, what if there's a space that your model doesn't cover? That would be a better explanation for the observations. That feels to me like a question about the model more than about the number of simulations from a given model that you need. But I'm not a cosmologist, so I don't know to what extent these models can actually cover the entire set of possible observations.
I would say though, Rafael, that is less of a concern for me, because if you're essentially defining your simulation grid based on the priors, then you're kind of forcing your model to be where you think it should be. Where I come from with this question is actually something that we encountered in a different issue, atomic data uncertainties. David knows this. Where we try to pick different realizations of atomic emissivities, line emissivities, and try to model observed data, but then realize that there were jumps from one to the other that were not adequately covered within the simulations. So that was the main question that I had. So it's,
right. So I think in those cases you need, I think it's you have to take a look at your data first and sort of and again incorporate as much as you can into the forward simulation. So you're limited by that choice at the beginning. So again, if you don't incorporate a very, very important observational effect, and then your data is subject to that, then your pipeline won't know what to do with the with, let's say, radio flashes or something really somewhat anomalous there. So I think it's a big problem with Bayesian analysis. Well, not a problem, but things that people bring up all the time is how do you know that your model covers all ground? And I don't think there's an easy explanation for it. But again, given the model that you've chosen, this is how to describe that distribution of parameters, or an attempt to describe them.
Hey, Lucas, could I just jump in as well?
Yeah.
My impression was it doesn't really matter because of your step 2, because you're enforcing a sort of minimum distance the simulation has to satisfy.
Mm-hmm.
So if it's a very important effect, that will make the distance very large, and therefore it's a bad model, right?
Right.
Well, if it's a bad model you're simulating from, nearly all your simulations will be discarded because the distance will be very large.
Right. I guess unless there's some sort of bias, if the effect was artificially pushing them in some direction.
Unless you had a bad model that happened to also create a similar observational effect, and therefore the distance is still small.
Yeah. So that's something that you have when you're designing these models. You have to sort of you have to be careful about what your data actually looks like.
And just that, what you just said, Raman, kind of forgets about the data compression too. So there's another, it's not quite so simple.
Yeah, exactly.
Yeah.
You lose a lot in the data compression as well, exactly.
Yeah. No, really good question though. Yeah, if there are no other questions, I'll proceed. So with this compression, so what this formalism for simulation-based inference sort of posits is this question: how do you define summary statistics or optimal summary statistics to describe your data in order to compute these distances, or as we'll see later, do density estimation for this posterior. So the sort of classic thing that people do for cosmological fields, especially CMB, so cosmic microwave background radiation, is largely a Gaussian field. So what that means is that you can take the Fourier transform of your observed density field and then sort of interrogate the field directly via a power spectrum analysis. So essentially the scale dependent variance of that field. And for Gaussian fields, all of the information in that field is contained in this power spectrum. And we call that a sufficient statistic. The problem is with large scale structure and messy observational surveys, this becomes a really tricky thing to do, especially when you have noise and survey effects. So essentially, when you take the Fourier you can freely take the Fourier transform of any field and interpret the power spectrum, but there is going to be a loss of information there, especially if there's some misunderstood effects from the survey effects, for instance, or things that are not highly non-Gaussian on a certain scale, for instance. So instead of doing, and the other thing is for massive fields, this power spectrum compression can be in itself super expensive, because you have to diagonalize the field and sort of invert these massive covariance matrices. So this also becomes a huge computational problem. So in lieu of a power spectrum analysis, what if we could compress the field down with, again, these would have to be very large networks, but a neural compression, so a non-linear compression down to an arbitrary set of summaries. And this is what we're building towards here. Before I go on, again, this is a general talk I give, so feel free to tell me if I'm beating a dead horse. But the formalism we're going to be using for our non-linear compression is an unsupervised training. So in order to make this mapping, we need to adjust the weights of our compression or arbitrary mapping via some criterion. And the criterion that we've chosen is to maximize the information content of the field, which we quantify using the Fisher information. So Fisher information of a given distribution tells us on average how informative some data D is about a parameter theta of a distribution. I've called it L for likelihood that models D. And this is one way to write down the definition. And this is best thought of as the curvature of the log likelihood. And this little cartoon here says that, okay, so the sharper the log likelihood surface at a given parameter value, the higher the information content. So that what this says is that at that choice of parameter, this model is very informative. This likelihood is very informative about the data that we see on average. So again, a very concrete, easy example to do is if you draw a set of ND independent data points from a normal distribution, which is parameterized by mu and sigma. You can write down the likelihood, which is just the product of those Gaussian distributions. And this should actually have this should be, actually, no, that's right, I put it on the inside. You can compute the Fisher information, which means you take the log of that distribution, and then you take the second derivative for each of those parameters. So the partial derivative with respect to each of those parameters. And you end up with this matrix form, which depends, in this case, only on the variance. And for a fit, you can compute the information, the Fisher information for a fiducial model, which in our case is just a choice of sigma, a choice of variance. The mean, so the information content of the field, just like in the CMB case I was talking about, only depends on the variance. And in this case, it's 1D, so we're only worrying about 1K mode, one variance. So again, this is just like a very concrete example when we have an analytic form of likelihood. But the question is, okay, what happens? Okay, and this is a really neat thing that tells us a neat theorem by Kramer and Rao that tells us that the minimal variance estimate for a given set of parameters, meaning sort of the best you can do, the best constraint that you can get for a certain model is lower bounded by the Fisher information. So if you know the Fisher information of your distribution at a fiducial model, you can compute minimal minimal, say, Gaussian contours using the eigenvalues of the covariance of that matrix that I showed you. So this is what people call Fisher forecasting. But what I wanted to get to is using the Fisher information in this information maximizing criterion. So again, what we're trying to do is take our giant field and compress it down to a couple of numbers that are maximally informative, these summaries. All right, so again, I'm beating a dead horse here, but we have this massive data space and we want to compress it down to, in our case, our cosmological model is going to be dependent on two numbers, two parameters. So we're going to compress it down to an R2 space, so into two summary statistics. And our F, if you see F flying around here, that means this neural network, this arbitrary mapping.
And just so was the choice of two numbers just in line with the fact that you're taking two derivatives, or was that just did you test out various dimensionalities?
So there's actually so Justin and Ben, two of the guys I work with, actually have a paper on data compression, and they show that you actually, so if your model, your simulator or your distribution depends on just two parameters, the exact sufficient the summary space needs to be of the same dimensionality as your parameter space, no more, no less, to describe that distribution. So if we have two parameters that generate this data, we only need to compress it down to two numbers. So does that answer your question?
Yeah, thanks.
Yeah, and in fact, so I'm going to provide the slides and such with to Vinay, and unfortunately I had a copy of this talk that got wiped when my MacBook broke, so I'm going to paste back in all of the references to these papers in case you're curious.
Is this a statement of two summary statistics only in the case we're using neural nets to decompress, or is that for anything?
That's it's for anything. I think it's just for an arbitrary. I think it's for an arbitrary mapping. They did it in the context of score compression, but I have
to. They don't have to be neural nets. Okay.
No, not necessarily. Not necessarily.
Okay.
Anyway, so the question is, okay, so when we don't have a likelihood form, right, for simulation-based inference, how then do we interrogate the problem in the context of an information maximizing scheme? Again, we want these numbers that we spit out, the X's of our network, to be maximum informative, to capture all of the information, all the fluctuations, all the stuff that's happening on the simulation level. So what we do is we create a mapping, which is in our case a neural network, that takes in the field, crunches it down to two numbers, and then in that R2 space, we adopt a Gaussian likelihood form to compute the Fisher information for training. So what our network does is it outputs a set of numbers for a suite of simulations. Some of those numbers are taken to compute the mean of the output of the network. Some of those numbers are taken to compute the covariance of those outputs. And then we compute at every training epoch this likelihood form, or more specifically, we compute the Fisher information, which takes which is given by this form here. So if we assume think of it as sort of at a fiducial model, a localized Gaussian likelihood form, from which we can then compute the Fisher information. And what we do is every single epoch, we show them the suite of simulations. We recompute the mean of the network outputs. We compute the Fisher information, and we back propagate until the Fisher information is maximal. So until this expression here saturates. And there's actually my advisor Ben has he calls it a research note on showing that through this mechanism, in choosing a localized Gaussian likelihood, we actually implicitly learn the unknown score, the unknown data likelihood score, and he has a nifty little proof that we're trying to shove into some research notes in the near future. So this choice of
Question.
yeah.
Just wanted to know. So if this is like a neural network, I mean, so is this done at every layer, or is it something that's imposed globally? It's only the
no, so it's done globally.
maximization.
So, yeah, so I'm actually this is the sort of the
Oh, okay, you'll deal with that.
really I'd only need to show this plot for the whole talk. But so this is the main compression scheme that we use for our analysis. We generate a bunch of simulations. Here we call NS the number of simulations in our suite. And then every single one of the simulations is passed through a neural network that compresses it down to two numbers. Again, some of those numbers are used to compute the means, and in our case, the derivative of the mean of the output of the network with respect to the parameters. And then some of those numbers are used to compute the covariance. So we can evaluate that Fisher we call it the estimator for the Fisher information using that little localized Gaussian form. So in this framework, especially if as we show for this cosmological case, if the entire pipeline is differentiable, we can obtain the exact gradients with respect to the mean. We can find the derivatives of the mean of the network with respect to the input parameters and compute this Fisher information exactly every single time. If we don't have, if you're working with simulations or a generator that isn't differentiable, you can do finite differencing, but that means you need to have a set of derivative data sets. So you perturb your parameters a little bit, generate a suite of simulations, and then feed those in as the derivatives of the mean of the network. But so what's very cool is we can compute this. If it's differentiable, you can compute this on the fly, because in JAX you can essentially press a button and you end up with your derivatives. I should actually, I'll build up the cosmological problem and I'll show you what we show eventually is that this actually saturates to the known Fisher information for these toy models that we're playing with. So this study is sort of a verification of this pipeline in the context of cosmology on toy models for which we know the answer. So we're really checking to make sure this technology lines up. So the example that we advertise is inference for mock dark matter fields. So in our case, we're using what we call the poor man's large scale structure, which is log normal fields generated from power spectra. Again, if the universe were really log normal, all you would have to do or log normally, if the universe is just a log normal correlated field, all you'd have to do is take the Fourier transform and interrogate the power spectrum. But here we want to verify the pipeline for which we know the answer. So again, in reality, it'll be much messier. So what we do to verify this is we train our IMNN compression on simulations out of fiducial model. So choose two numbers and we generate a big suite of simulations. We then create an observed universe that's far away from the fiducial. So we're going to choose two other numbers to generate our universe. We call those two numbers theta target. And again, in a real analysis, you wouldn't know that. And then using this compression, we're going to simulate more other universes over a prior range, and hopefully, and later we'll show you some density estimation for this posterior that we want. So this is sort of the roadmap. So again, the model that we choose is just a power spectrum. It's Eisenstein-Hugh linear matter power spectrum. And we vary two parameters. So we vary our critical matter density and our and sigma 8. So, and our fiducial model. So the cosmologists in the audience will sort of scream at this choice of numbers. It's chosen to be deliberately far from what we know to be sort of a realistic universe. A realistic universe should be a critical matter density 0.3, 0.28, and a sigma 8 around 0.79-ish. So what's cool is that it's a really nice plot that actually shows if we write this in JAX, we can obtain exact gradients, and this is sort of an intermediate gradient from that network scheme that shows the gradient of universe realizations with respect to our cosmological parameters, in case you were ever curious. So we do this IMNN training, like using that architecture that I showed you. And what we, again, because we know the answer to this problem, these log normal fields, we can compute the Fisher information for the fields exactly. that form is known for log normal fields. And we show that the unsupervised network actually saturates to the theoretical field information, the limit. So once we have this compression that we know is maximally informative, we can then proceed to doing some cool inference. So now we have a way to crunch our numbers, our universe down into two numbers. So what we can do is observe, pretend to observe the universe at this set of target parameters. We use Planck, sort of the ground truth, as it were. And what we first do is we can make score estimates of the parameters. So this is used to sort of like a Newton step, where using the outputs of the network and the outputs of the network for the observed sky, we can sort of walk back from the fiducial parameter. And what this looks like here, this is sort of a map. So we've chosen a really, really bad fiducial model for our universe right out here, 0.6.6. And what we've then done is walked back using score estimates. We walk back, and our score estimates actually put us pretty close to these crosshairs, which is what our simulation truth. What we can then do is, again, the network spits out a Fisher information. We get that for free after we've trained. We can use that Fisher information to give us sort of a Gaussian approximation for how fat our posterior is going to look. So, and we center that at the score estimates. But even before we make an inference, this is all deterministic. We don't have to do any sampling or anything. We already have sort of a forecast for how tight our parameter estimates are going to be. And that's sort of given by this ellipse here. So now the next step is to, well, in a real analysis, if you choose a really poor fiducial model and it moves this much away, so again, it's outside of this ellipse, it's in your best interest to retrain on that new score estimate. And because this is a black box, and we don't know how this we don't know how well this poor fiducial point will capture information if you use that compression for inference, seeing that the score estimates have jumped so much. So it's in our best interest when we don't know when we don't want to impose any prior understanding of the universe to retrain if our estimates move a lot. So we choose a new fiducial model. We train it at these much closer to target cosmological parameters, so we have a better description of better compression for our cosmology. The next step then is sort of my favorite part of the whole scheme, is doing neural density estimation. So what I showed you guys before with implicit likelihood inference is sort of the brute force approximate Bayesian computation approach, where again, given your compression, you define some arbitrary distance measure, and you accept or reject simulations based on that distance measure. But here, this is a much cleverer way, and actually we show a much more efficient way to cover that prior range and obtain an actual posterior distribution using simulations. So what we're going to do is actually parameterize our distribution using conditional masked autoregressive flows. So what we're going to be doing is, again, from Bayes' theorem, we know that P of theta given our summaries is proportional to P of the summary data likelihood, so P of x given theta. What we're going to do is train a parameterization of this summary data likelihood and as a function of theta over the prior range, and then evaluate the posterior using this using a simple MCMC. So what's cool about conditional masked autoregressive flows is that there are neural networks that are carefully masked to ensure an autoregressive property. So using the chain rule of probability, if you have a bunch of summary statistics, you can decompose your your likelihood, your distribution into a product of conditionals. And what we can do is we can model these conditionals as sort of a set of means and standard deviations, and minimize the log loss of the output of this network. So this is a good diagram. This is from Justin's Delphi paper, density estimation, likelihood-free inference, using this sort of technology. And again, he's labeled data summaries as T, but this is our X in our case. What we do is we feed in a densely connected neural network that again is masked to ensure this autoregressivity property. And what's cool is that this dense network expresses interactions between changes in the summaries and changes in the parameters over the prior range, and arbitrarily parameterizes a set of means and standard deviations. And what you can do is take these MAIDs, the mass autoencoder for density estimation, and stack them. So what you end up having is sort of what we call a neural flow, which is a very good, a very descriptive way of parameterizing funky distributions.
Sorry, Lucas, quick question. Yeah. Can you explain what masking has to do with autoregressive properties?
Right. So if I go back to this this definition here, this property holds so long as these indexes are respected. So every time I increase this, so when I becomes 2, this has to go 1 to 2 minus 1. So that's what we mean by ensure that the masking preserves this property.
So okay, I mean that sounds like ordering, right? I mean, how is that?
Yeah. But I guess the point is that we're not feeding it into an arbitrary dense network that connects every node to every node, to ensure that this property is satisfied. So what's cool? An easy way to think about this is a function that you can train that parameterizes this conditional distribution. So what we're going to do is, once you have a trained neural density estimator, you can sample for theta given a set, sample for X given a set of parameters in a prior distribution. So I'll map it out here in the context of our study. So as we showed before, we have this trained compression, which hopefully is pretty close to our ideal. Well, we know in this case it preserves the information of the field. So we generate a whole bunch of simulations drawing from the prior. Again, this mapping is done at a fiducial model, but we can still feed our simulations drawn across the prior through the mapping to create our x1 and x2, so our 2 numbers that we spit out. And what we do is we also feed into this mass autoregressive flow the corresponding cosmological parameters that generate the simulation. So we're sending in these pairs of parameters and summary statistics. And what we do is we minimize the log loss. So this in the Delphi paper, that's shown to be equivalent to minimizing the KL divergence between the estimator for P of X given theta and the target distribution, the true underlying one. So we end up with a parameterization of this summary data likelihood. And what's very cool is that once we have that, this is just like drawing from a bunch of normal distributions, which in NumPy, given a random number generator, you get for free. So you can just press a button and you end up with an X evaluated as a function of theta from that distribution. So once you have this cheap way of drawing from this neurally parameterized distribution, you can then run a really cheap MCMC where you draw from the prior, and then you draw from P of theta, you plug in your theta to your distribution, and then you sample you sample your summary data likelihood around your evaluated X target. So what we've done here, we take our target sky, we crunch it down to the same, to a set of two numbers, and then we evaluate we do just an MCMC around that that target value. And again, this is you can draw from this cheaply, just as you would from any normal distribution. And what you can do is build these, and then you build your posterior. So what this is really just a bunch of scatter plot, but we've done a KDE to smooth it out. And what's very neat about this choice of posterior parameterization is that you can actually continue training your network. So you can draw from the posterior. So once you have this set of points, you can draw a set of them, re-simulate a bunch of universes, compress them down using the IMNN, feed them into the same network, and continue minimizing the loss, so that for your target sky, you actually tighten your contours over time. And I think the biggest advertisement for this scheme is that it's much more computationally effective than approximate Bayesian computation. So this is a cutout from our one of the final money plots in the paper. These fields are two realizations generated from the same target model, this plot here sort of summarizes the entire story, right? We chose a poor fiducial point. We then made our score estimates, which are at the star. We retrain the compression, and then we evaluate, we do the density estimation. And what we did for comparison was just do a brute force approximate Bayesian computation over that prior range. And what we found was that we need an order of magnitude fewer simulations to do the density estimation to get these nice tight contours than we do to get these the scatter of accepted ABC points. So ABC over the chosen prior range took roughly 12,000 points, and the Delphi training, the density estimation, took around 4,000 simulations per target sky. So that's a massive reduction. And if I did my math in my head right, it's a factor of 3 order of magnitude improvement. Sorry, factor of 30 improvement. But the order of magnitude is what counts in this case. And I think Aneta has a question. Sorry, if I missed any of the questions, I'm sorry. I minimized the chat here.
Yeah, so I have, I don't know, you probably said that, but I was wondering, how do you get these contours on the final parameters? So I see the simulated points, but is this based on the number of simulations you've done, and how do you get the contour uncertainties on that?
So do you mean the blue, the red, or
yes, the blue, and then basically the confidence contours, or whatever you call that.
So both both the red and the blue here are actually scatter plots, but what we do is a kernel density estimation smoothing, where you essentially think of it's sort of like a nearest neighbor thing, nearest neighbor algorithm, where you can we basically fill in the gaps between points. What we want to emphasize here is that, again, once you have this really cheap neural parameterization, it's a very, very cheap, you can evaluate the posterior by an MCMC in almost no time. So the blue contour is something like 50,000 points smoothed out using a Gaussian KDE. And the approximate Bayesian computation, I think, if I recall right, something like 400 points. And that took 10,000 iterations just to get 400 accepted simulations mapped onto this parameter space. So again, we left, I guess it's another form of advertisement. We left the ABC as a scatter plot to show you how many simulations it takes to get so few points. Whereas the neural density estimator, you have if you really wanted it, I could send you the network weights and you could just sample all day long for free.
No, but this is I'm trying to understand whether this relates to uncertainties, or is it just the number of the draws which you get, right? Because what's the thinking about the likelihood and the intervals related to the maximum likelihood, which we think about 90% or 95% interval. How this relates to sort of standard understanding, because you have, as you said, these are just the simulations, and kernel density estimates gives you the shape of that scatter plot.
Right. So you're saying how many simulations you need to be sure you can define your.
Yeah.
So and that's something that I actually don't have a super good answer for. So with approximate Bayesian computation, I think it's usually, to be honest, when I was running these experiments, it was just sort of, I would just look up what other people the number of points that other people had reported to fill in to consider it a good 2 sigma or 3 sigma bound.
Right.
And again, like around the neighborhood of 500 simulations for a 2D plot like this seemed about right. But that's another problem, well, an issue with approximate Bayesian computation.
Right.
How do you define how many simulations do you need?
Right.
And I guess with the neural density estimators, again, it's people could raise an issue with okay, network parameterization or sort of an arbitrary choice of weights. But what's cool is that you actually have a distribution defined, and it's not, again, you don't have to, I guess, if you wanted to increase the number of points to estimate your distribution, you don't have to destroy a couple of GPU towers to do so, running the simulations again. And I should say that, no worries. And I should say, I guess I didn't mention, but when we do this neural network training, we actually we train a bunch of different architectures for this MAF. So we actually, in the paper, we train 5 in parallel using a different set of weights, so a different number of weights for each one. So it's 2 with 2 50-50 fully connected layers, and then 3 with 3 50-50 connected layers for this parameterization. So the idea is, okay, and then the posteriors that you see in the paper are actually just concatenated posterior estimates, so average posterior estimates over this space of possible networks. But again, if you use a single network, you might get a very, very good posterior estimate. But again, with machine learning algorithms, you want a sort of epistemological understanding of what the space of networks looks like. But so I guess my sort of this is the final plot.
By the way, Josh has a question.
Sure.
Josh, do you want to ask it?
Yeah, so I just put them in because I actually have to head out in a second. But I was just curious about the error quantification from using sort of, Delphi here versus ABC. So in ABC, you have this nice way of sort of tuning the error in your approximate posterior by, adjusting epsilon. And obviously, once you use this, normalizing flow-based estimator or neural flow, now you have sort of some type of error that comes into the approximation. And I'm wondering if you looked into this at all.
So right. So I guess so for the purposes of this paper, we use the ABC as sort of the benchmark, right? So again, ABC you can fine tune. It's very expensive, but you can fine tune it. And we compared the right. We compared the Delphi estimates to the ABC. The other thing is, I guess, a metric we can use is, again, these Fisher estimates. So this Fisher here is generated using the IMNN's Fisher. So in practice, your Delphi, your posterior contour should be about as small as the Gaussian approximation. Again, it will be stretched in some funky way. That's sort of the reason we're doing the Delphi estimate. But that's another qualitative gauge we use. And other than training over a space of models, and also ensuring that the log loss isn't decreasing anymore, I don't know that there's any other way to enforce that. But that's something that did kind of bug me. So I appreciate the question.
Awesome. Thanks so much.
No worries. Casey.
Oh, hey, Lucas.
How are you doing?
I'm all right. A question which you might have answered, I came halfway through. But when you're training your various neural networks, is your goal actually to minimize your objective function? And the reason I ask is because since deep networks often are parameterized, it's often the case that you don't actually want to minimize it. In fact, there are various tricks like early stopping or dropout or weight decay, which are designed to keep you from actually minimizing the function, the objective function you've written down. So are you actually using these regularization tricks, or are you, or not?
So not in this specific study. The original Delphi paper did do dropout, if I recall right. What we did was just do we did a sort of the deep ensembles approach, where if you have a particular network configuration that gives you an absurdly low loss, that's very obviously over parameterized, but then in our 4 other networks that give you a much more consistent and higher loss rate, you concatenate all of those together. They've all seen the same data. And you concatenate their posterior estimates together in order to represent the spaceable models. So it's a way to get around it, but it's, again, there are different types of regularization, of course.
Okay, yeah.
Yeah, it's definitely not. We did not exhaust the early stopping and regularization possibilities.
Right. Thanks.
No worries. Again, I guess I'm more or less all the way through my slides, but again, this was sort of the big this was sort of the advertisement for the method, where we cut down the number of simulations needed for this rather high dimensional data compression problem by an order of magnitude. And I guess I can give you guys a roadmap of where this sort of analysis is going. So a big topic of my first big thing that we're going to work on for my PhD is to strap this existing pipeline to much more intricate and expensive large-scale structure simulations. So we have a particle mesh code that we are currently adapting to be in JAX to do the exact same analysis, but using a much more articulate simulator. And we want to interrogate the information content that we can extract, and then also see what we can see what this sort of compression can tell us about the input parameters. So again, the fields that we've done here are toy models. I can't emphasize that enough, the poor man's large scale structure. So the eventual goal is to build this technology sort of with the idea to eventually interrogate real data. But I guess the other thing I really should have mentioned from the get-go is, I know a lot of folks in this on this listserv are not cosmologists, but this sort of inference can be done for sort of any science where you have a decent simulator. So if you have a simulator for an effect or a set of data that you want to to interrogate, as long as that simulator takes as a function of a set of numbers that mean something, you can adopt this sort of formalism. So the original IMNN paper is called Automatic Physical Inference, using information maximizing neural networks. And again, if you provided you do a little bit of network tuning and you trust your simulator, you can do Bayesian inference in a remarkably cheap way for a whole host of problems. It doesn't have to, this just happens to be the first time we strapped all of this together for a cosmological problem. And I guess the last thing I should say is, I don't know if I want to, I could share this, but we also have a public tutorial code. So all of this entire analysis, in fact, can be run on a single GPU on Google Colab. So what we've provided is we provided scripts to both train an information maximizing neural network and also to do this density estimation. And we did this in tangent with in collaboration with Quarks to Cosmos at CMU. So the code is, I think I shared it with Vinay. It might be at the end of the email, but I share my.
It's the link is on the web page.
Yeah, but if I share my, oops, 1 second. So all of this code can be run at home on a free Google Colab account. Again, we walk through the entire analysis. You can do the entire experiment, and again, if you want to impose some regularization for the networks, be my guest. I'd be happy to know if you get different results. But this is sort of, this is in an effort to make the code transparent and public. And in fact, well, the story behind the Google Colab is actually because I got kicked off my cluster and had to finish my master. So I had to figure out a way to get it to run cheaply. But the side product is you guys can play around with it. So I guess so that concludes my set of content, but I'd be happy to stick around, and if you guys want a code demo, I'd be happy to show it. But
hey, thanks, Lucas. Nice talk.
Thank you.
Are there any questions? I guess
I was confused about something. I'm sure you talked about this, but I missed it. On the neural network, the first neural network that creates these summary statistics, do you need lots of simulations for that, or you only have one simulation for one set of fiducial parameters?
Right. So here again, so here the network that we published in the paper required 200 simulations, but we did this, we say, on the fly. So we showed the network a new set of 200 simulations every single epoch. So if I show you that training curve, the network has seen quite a few simulations. So right, 200 times, well, in our case, 3,000 is basically where it's saturated. Again, this is cheap to do. We wanted to verify this pipeline using, again, in an unsupervised manner, using new realizations every time. But in a real analysis, you're probably going to be limited to order 10,000 simulations. So in that case, you would need a validation set. And you would probably want to show more simulations per iteration. But again, this was just a, I don't know what happened there. This was just to verify the pipeline.
And what is the reason that you need so many simulations, or even more than one simulation at the same value of the theta?
Right. So
is that because you need the sampling distribution of the positions of the galaxies, or whatever it is?
So that goes back to like the definition of the Fisher information. So the Fisher information is the second derivative of log likelihood, but it's an average over a bunch of different realizations of the data. So in our concrete case here, The Fisher information doesn't happen to depend on the data or anything. It only depends on the variance. But if you don't have that form, all you can do is compute, again, our estimate for the Fisher information, which, sorry, I'm going out of order here, is compute our sort of estimator and then average that estimator over a bunch of different data realizations.
So that's the 200 simulations. You average it over 200. Average that second derivative over the 200.
We compute the mean over. We take 100 simulations to compute the mean, 100 simulations for the covariance.
Okay.
And then we compute this this Fisher that way. So does that answer your question? So the Fisher information is an expectation value for the log likelihood curvature.
Yeah, I think that makes sense. But so then, when you compared it with the ABC, and you said the ABC takes 10 times more simulations, does that incorporate the number that you need for this?
That does not. So that's just purely to obtain the posterior distribution.
Okay, because with the ABC, you would still need this first neural network.
Exactly. So I guess the caveat to all of this is that you do need a lot of simulations to train the network, but it's not, again, if you take for a suite, let's say you had a finite suite of 5,000 simulations and a validation set of 2,000, for instance, and you did this scheme, and you can picture a validation curve here on the validation set. That would still keep you under that budget, that ABC budget of 12,000 simulations. Does that make sense? So the idea is to keep the budget of needed simulations down. But that's something that we're actively investigating. When we increase the complexity of the simulations, it could be that we hit a dead end where we don't have enough simulations in our pot to get a good estimate for the Fisher information. It might mean that we need to order a whole lot more, but this is already a pretty promising result, at least on the density estimation side.
Mm-hmm.
Because I think the problem with the density estimation or the posterior estimates is that you can easily and cheaply, once you've chosen a Fisher model, generate a whole bunch of simulations at that point, where the expensive part is simulating too many times over a really fat prior, because then you're just throwing away simulations. You're throwing away precious GPU hours to create them.
Mm-hmm.
So I guess we're being smarter about where we want to spend our GPU hours.
I had another question too, but I'll let other people ask if they have questions.
I think you can go ahead, Alex.
Okay. I just was wondering about, do you think this will work well, or how well it will work, or anything, if the situation is multimodal, if the likelihood is actually multimodal?
Yeah. So in fact, so you mean the posterior,
like the true likelihood that's totally unobservable, but or on the one that you can't write down, but just the likelihood as a function of the model parameters.
Yeah. So the target distribution. And do you mean okay, yeah. In that, I think plausibly, yeah. Plausibly, yes. So in fact, Tom Charnock, who was on the original IMNN paper, has written a bunch of supplementary documentation for the software that we use, and that's linked in like this GitHub and the paper, where he's done some somewhat funky, again, 1D cases where the unknown data likelihood is a mixture Gaussian, for instance, where you have like a two peak situation, or a set of disjoint Gaussians, and it worked reasonably well. Again, this is not published, but Again, with any of this, the statistical framework, it is sort of trial and error. Again, I can't, I'm sure you could concoct something that's just unreasonably difficult to sample in general. But so far it's been, it's proven okay. So, and I guess that to add to that, this choice of sort of pseudo likelihood form in parameter space, one that we use to compute the Fisher, is actually what Ben Wandel has written up, and what we're hoping to put out very shortly, is that this is actually, you can show that by enforcing this likelihood choice, you actually implicitly learn the score of the unknown likelihood. So maybe you don't learn the exact say double peak data likelihood, but you actually implicitly learn the score of that under the hood. And I guess the idea there is that, okay, if you learn the derivative of the log of the likelihood, you have a reasonable descriptor of the distribution, even if it's sort of funky and multimodal.
I think only if it's Gaussian you do.
No. This is a general description that Ben's put out. I wish I could, again, it's not mine, so I can't. I wish I could. I have the print, but we're about to stick it out.
I just mean that this score number might not be very useful.
Right. So, yeah.
The actual distribution is multimodal.
Right. Oh, so I see what you're saying. Yeah. So it's as long as this, well, if the score tells you enough about that distribution, then you have a good descriptor. But if you don't, then you might have found, that might be a tricky scenario.
Okay, thanks a lot.
Yeah, no worries. I mean, honestly, there are plenty of examples, and honestly, Tom has made it very, very streamlined. We pull from GitHub repo and play with the software. Like, you can, if you concoct something and do this compression, let me know how the inference turns out. If you run into something that just doesn't work, then Tom and I can hop on it and see what's up.
Sure. Yeah, of course.
All right. Any other questions? If not, I have one small follow-up to what Alex was asking about. How well would it work if our simulation models were stochastic?
How do you mean?
Meaning, for a given parameter input, you can get different realizations, many different types.
I mean, so you mean if the variance of possible dates, if the data is really, really, really variable, you mean?
If the data can be highly variable. I mean, imagine something like flares on a star or something, right?
Yeah. So again, as long as you generate enough simulations that capture that variability, I think that's where you choose the simulation number. So for our universe simulations, every single one of those is stochastically realized. They don't happen to, again, to our eye, they don't happen to look very super different. You can find features, especially in the log normal fields, that look different than a neighbor in the suite. But again, I think as long as you, again, if a really, really wacky flare happens every 5,000th instance, then you need 50,000 simulations. However many, if that gives you if those weird events are indeed important to your inference. If your choice of initial conditions for your flare.
So there is some reliance on the central limit theorem. Okay.
Definitely.
Okay. Any other questions? We are close to our allocated time, even though we lost about 15 minutes in the beginning. So thank you again, Lucas. If there are no other questions, then well, thank you again. So
thanks, guys.
Nicely done.
Thanks.
And so send me let me turn off the recording. Where is the recording?